Alright, in this video we will look at how to calculate and how to present the Mandelbrot in Blender and also the explanation of the mathematics. It's actually not as complicated, and also the Julia sets that arise from the Mandelbrot and also the burning ship fractal, which is a very strange looking fractal, pretty cool. And we will do this all with Blender notes and project files in the description of this thing. So we will do something like that today, and we will also start by explaining how this thing actually works. Right, so let's open up a new file and file new general, and I'm just gonna add a plane here. And we're first gonna do this explanation part, right? So at the Mandelbrot set, right? So if we go to Wikipedia, right, here we can see the page of it, and we can see that the function is that the Mandelbrot set is a set of complex numbers, C, for which the function, I'm actually going to make this larger so you can see this better, for which the function z equals c squared plus c does not diverge to infinity when iterated from z equals 0, right? All right, so this is something we will do. This is the function here, right? Z equals c squared plus c. So what this actually means is that I'm just going to draw here, right? Add a new material. I'm going to delete this principal thing here. And what this actually means is that if you have, let's say, like a coordinate field like that, like usually you have, I mean, I think you're familiar with it. We have one right here. We have y and x, right? And then we have z coming towards us. We don't care about this right now. Mandelbrot is two-dimensional. We can make this kind of like a little bit three-dimensional afterwards, but it's mostly two-dimensional. Now, in the center here, we have 0, and then we have 1 and 2 and 3 and 4. And down here we have, of course, -1, then -2, and -3. And up here we have -1, -2, -3. Sorry, just ones, just positive numbers. And then here we have also negative numbers, right? So this is pretty clear. I think you are all familiar with it, right? Now, the thing with Mandelbrot is that in order for this thing to appear in the center here, you know, this shape of Mandelbrot, we actually have to use not real numbers, but complex numbers. So instead of this real axis here, we will instead use a complex axis, right? So we have 1i, 2i, 3i, and -1i, and as continues, -3i. So what is an I for the first reason, right? Well, the I actually is the square root of -1, right? So as you know, there is no such thing as a square root of -1, because this implies that we have something that we will multiply with itself, and the result will be -1. But it's impossible, because whatever we multiply, for example, if you multiply -1 times 1, we get 1, right? But these are not the same things. And -1 times -1 is 1. So whatever, sorry, -1 here. So whatever we do, actually we cannot get two same things multiplied and have -1 or anything negative as the result, right? So this is something that is the property of the complex number I, right? And this is usually like described as a second dimension to numbers. So you have like, let's say you have like a negative side here. Here you have the negative, and on this side you have the positive, and then the complex numbers are like on an angle going through here, right? So this is the complex side of numbers, right? And going also down here. So this is like under a 90 degrees angle or something like that. So this is kind of like a brief introduction to complex numbers, but what we care about actually is how to make the Mandelbrot, right? So the function for the Mandelbrot, let me write this one down, right? This is z squared plus c. Right, this z can be anything. It just means something like a thing we have to square, right? So this means that, and the c here is a number that is same all the time. So for example, in the start, the z here is 0, right? So it's 0 squared plus c, right? And in the next iteration, we will then have c squared plus c, which equals like, then I'm just gonna write this down like that, c squared plus c. And in the next iteration, we're then gonna have c squared plus c. This is again squared, and then again plus c, right? And as you see, it goes iteratively on and on and on. And this is how, and then we measure if this thing goes to infinity. So I'm gonna show you with a real component here, right? So to create the Mandelbrot set, we have to just choose a point on this complex plane, right? Complex numbers in this way, and real numbers here, imaginary or complex, this means the same thing, imaginary numbers here. So let's say we select this point 1 here, right? So if you would like to express the like coordinates of it, this will be 1 for on the real number axis and 0 on the imaginary numbers axis. So we don't actually have to write down anything about the imaginary thing right now. So let's iterate this, right? So first it will be 0 squared plus 1, then it will be 1 squared plus 1, which equals, of course, 2. Then it will be 2 squared plus 2 squared plus then c again, right? Which is again 1. And because c is this one here and z is this one here, and this will equal, of course, 5. The next one will be 5 squared plus 1, which is 26. And the next one will be 26 squared plus 1. And now I just give up because I cannot calculate this anymore. But you understand the principle. And as you see, this tends to go to infinity because it keeps going larger and larger and larger. I mean, it's not sure until we calculate an infinite amount of iterations, but I am pretty sure it goes to infinity, right? So this number will not be part of the Mandelbrot set. Unlike, for example, 0, which will be part of Mandelbrot set, because if I do like 0, I'm just gonna redo this for the sake of an example. If I do 0 squared plus 0, this will be 0, right? And in the next iteration, we'll use this 0. This will be again 0 squared plus 0, 0 squared plus 0. It will be the same thing all over again, which means this number is part of the Mandelbrot set. And in fact, if you go to the Mandelbrot function, this complex plane center is here. So you see this number is well part of the Mandelbrot set, right? Now, how do we do this in with other numbers, right? For example, if you have here this thing, yeah, this is 1 and 1i for the another coordinate. So for example, if you have this point here, the coordinates for this point will be, let's say this is point A, and this will be like 1 plus 1i, right? So this will be 0 squared plus, then the complex number, 1 plus I, or 1i, it's the same thing. In the next iteration, we will have 1 plus I squared plus 1 plus I, and go on and go on. I'm not going to do any calculations with them right now because we are going to discover soon how to calculate with complex numbers, right? So this is the thing. And actually, if you're using a programming language, like for example Python, or I think actually on Wikipedia we do have a pseudocode of calculating a Mandelbrot. Let me find this one really quickly. Yeah, we have this here, right? So actually this one is done without complex numbers, right? So this is not an example, but actually in programming languages you can just use complex numbers as numbers to multiply and do some mathematics with, and it will calculate the correct answer with them. But in Blender, you know, under this math section here, converter math, we actually don't have any complex stuff, right? It just calculates with real numbers. So this means we have to we cannot use or just square this complex number. We have to do the multiplications or our mathematics separately for the real component here and for the imaginary component here, which means for the real, which is the x, and for the imaginary, which is the y, right? We have to do our mathematics separately. So let's do this separately, right? I'm gonna show you how this works. So first, of course, we need our real axis, right? So this is our texture coordinates, right? Take texture coordinates, and we go down here, and we have there the object coordinates, right? Let's go to render view with AV, and we see this looks like that. And let's separate this, right? So now we have the x-axis, right, which is our real axis, and y-axis, which will be our imaginary axis. Of course, right now these are both real axes because, I mean, if I, for example, multiply those together, or I add those, for example, together, or multiply, I mean, Blender doesn't know this y part here has to act like an imaginary component. It's a square root of ones, like going up here. It just acts like a, you know, like an ordinary, normal, real number. So let's see, how do we have to calculate this? So the formula is, again, I'm going to write this down, c squared plus c, and the c is made of two parts. So I'm gonna write this down again, z plus, right, x plus I, y, right? So the real component and the imaginary component. I mean, this is the exact same thing here, right? As we were doing before on the complex plane, for example, 1 plus I, right? This is the shape of an imaginary number. So the next iteration will imply that we square this thing, right? So we square this thing here, 1x plus I, y, and now we have to, I mean, add the c again and all that stuff. But we have to tell Blender how to square this thing here, because this is not as easy as just taking, you know, adding them together, right? X plus y, as you see, and then adding a square or a power 2, right? This is not the real correct answer, right? Or not the real, but the correct answer. So let's do this first with real numbers so that we can get the hang of it, right? So for example, if I just have x plus y and I have this squared, this is the same as x plus y and then x plus y, and I'm running out of space, right? So this is the same thing. I think you agree with me, right? If you don't agree with me, you can see the proof here. 3 plus 3, for example, or let's make the different numbers, right? So that it's not prone to function. So 3 plus 4 squared, it's the same as 3 plus 4 times 3 plus 4, which is, I mean, 7. This means 7 times 7, right? I mean, you can see it's the same thing, right, with numbers. So, how do we calculate these things, right? Right. We have to do so that we multiply this one with this one, and this one with this one, and then this one with this one, and then this one with this one. So let's do this, right? First thing, x times x. This is x squared, of course. X squared. The next thing, x times y. All right. So plus xy. The next thing, y times x plus y and x. And then the last thing, y times y, which means y squared. Now let's make them a little bit easier to understand. So x squared plus 2xy plus y squared. I mean, you can see x times y and y times x is the same thing as, you know, 3 times 4 and 4 times 3. It doesn't matter, right? It's the same thing. So I can just put those together like that. All right, and this is how we do things with real, oh, sorry. This is how we do things with real numbers, right? It is understandable. I'm gonna go back a little bit. I'm gonna redraw this line here, this box. All right, this is how we do this. Now with imaginary numbers, this will be a little bit different, right? If we have this I times y here, right? So let's do this with imaginary numbers. Let's see what the difference will be. So alrighty, let's do x plus I times y, and let's square this, right? So this is again the same thing as x plus I y, and again x plus I y. And so now we just have to do the same thing as before, right? We multiply like that, and we multiply like that. So the first thing is x squared, right? X squared. Then the second thing is xiy, or I mean the order doesn't matter, right? It's just we can do like, for example, x, y, and I mean, because the order of the multiplication doesn't really matter. So this one here and this one here, now it's iy times x, which is the same thing, right? X, y, and I, all the three components. And the last thing is iy times iy. And now the question is, how do I multiply I with itself, right? Well, I'm just gonna first write this down as, you know, as everything here. So it will be plus I, y, I, y. Now let's make this a little bit simpler again. So x squared will be x squared plus 2x, y, and I, right? And then here, let's see what we can do. Like, this is essentially the same thing as we would have 3 times 4 times 3 times 4, right? So this is the same thing as 9 times 16. I think you agree with me, right? Because, you know, 3, 3 and 4, 4. Or it's the same thing as 3 squared times 4 squared, right? So this is, I mean, I think I understand what is happening here. So we can do the same thing here. This is the same thing as I squared multiplied by y squared. But what is I squared? Well, as you remember, because I is equal to the square root of -1, this means I squared will be -1, right? Because this will be the same thing multiplied with itself. So for example, if I do square root of 3 times square root of 3, this will be 3, right? Because square root is essentially like, if you multiply with itself, you get the thing under the square root, right? So this means I squared is -1, which means we can rewrite this thing as x squared plus 2xyi plus brackets minus, okay, I'm just gonna make this, I mean, I'm not so sure how familiar you are with calculus, so I'm just gonna write this down like that as the first thing, right? And then we can simplify this even more, right? So x 2xyi plus squared brackets minus y squared, right? Because whatever I multiply with -1 will be just minus the thing, right? For example, -1 times 3 is -3. We don't have to write this down like that. And now we have plus and minus here, and this actually means we can simplify this even more with 2xyi minus y squared, right? So we can put those together like that. So this is the last thing, which will be how we multiply this if this was a complex number thing, right? So let's compare this. Is this a similar thing? X squared plus 2xy, here we have an I, and the last thing is subtracted instead of multiplied. And this makes the main difference, right? So, and as I told you, as you remember before, that for this C component here, Blender cannot do like complex multiplication, so we have to do things separately for the real and the imaginary axis, right? So let's just separate the real and imaginary components from here. So what are the real components from here? The real components is x squared, right? And minus y squared. These are the real components, don't have any I in it, right? And then the imaginary components are 2xyi, right? 2x and y. And we don't have to write this I here because this just acts as an imaginary component. I mean, we don't have to write this down here because we don't, as I told you, have access to this number in Blender, so we just can remove this right now. The point of this multiplication was to basically make the numbers obey to the rules of imaginary calculation so that, this thing here is subtracted instead of added, right? And we found this by using the imaginary component. All right, and now let's put this formula down then. We have x squared minus y squared, right? So first, of course, we have power, right? So x power 2, and we have then y at the power of 2, right? And we're gonna, what are we gonna do with those? X squared minus y squared, right? So we're gonna do, actually I think it might be easier for you if I just make the viewport like interface a bit larger, so like 0.35 maybe. All right, so x squared minus y squared. So we subtract them and we have a thing like that. All right, and this is now our real part, right? Real component of this c number here, right? That we're gonna square. Multiplications for this, for the real part of this calculation. So Ctrl J, F2, and let's call this real. All right, I'm actually gonna call this Mandelbrot. Blend, just to save this. And what do we do with the imaginary part? 2xy, right? So we take this, we multiply first 2 times x times y, all right? So I'm gonna just multiply x by y, right? And I'm going to multiply this with 2, right? So this acts like that. So basically what we're doing right now is, as we have this kind of our like complex plane here, right? We have separated the complex number. The vector acts just like a complex number right now. And we do the multiplications for the real part of this complex number and then for the complex part, right? So this is imaginary, which means complex, right? And now what is the formula, right? After we have squared the thing, right, we are again gonna add the c, right? So we have to have some addition here. All right, so I'm gonna add the c again to the both of the parts, right? So this is the real part, so I'm gonna add the real part of c to here, and the imaginary part of c to the imaginary part of our calculation, right? So I'm gonna do like that. And now I'm gonna add the c, right? So the question is, what is the c? So because we're using the x and y, this means that, for example, if I take like a point, like let's say this one here is the 0, and then again like 1, 2, like this here is 2, and this one here is 2 plus I, right? So if I start to calculate for this point, I'm always gonna add the number of the original coordinate of this point back to it, right? And this makes a Mandelbrot set. If you add something different, this will create a Julia set, which looks pretty cool, and we will get to this later on. But so to add the same number or coordinate of the same point back, we can just, take the x and put this here. But because this has to stay the same thing throughout our iterations, I'm just gonna duplicate this, right? And I'm gonna bring them in from a separate part. So I'm gonna bring the x, which is our real value, from here, and y, which is our imaginary part, from here. I'm gonna add a reroute to make this more understandable, like that, and I'm gonna add a reroute also here and also here, so this is more readable. This looks pretty nice, right? So here we add the C's, right? So I'm gonna put those together. I'm gonna Alt S shift the sockets. It doesn't matter, right? Addition is indifferent to the order. So we're gonna call this add C, right? Here we add the C. As you see, we just have added the C, and then this is actually ready, right? So I'm gonna move those things down a little bit here. And now what we have to do is to put this thing, we have separated the complex number, right? This was our complex plane, right? We have separated it into real and imaginary parts, done the calculations. Now let's put this back together with a combine x, y, and z, right? Actually, what we can do is just put Control H here, because we don't need the z part. Mandelbrot is two-dimensional, and put this is the real part, right? real to the x, of course, and imaginary to the y. And let's see how our coordinates look. They look like that. So before they look like that, now they look like that. Something is happening, right? So now that we have the calculation done here, right, everything is flowing nicely. What we're going to do is that we are going to iterate this over and over again. So how do we do this? We are going to first group this, right? So I'm going to just drag over all of this thing here. I'm just going to maybe show you the nodes on a larger screen here, right? They look like that. And now I'm going to select all of those except the object coordinates here, the extra coordinates. And I'm going to press Ctrl G. G, right. So the thing that's going on from here, the upper part, will be called our Z in the formula, and the thing down here will be called the C, right? And then from the output, we will be getting the Z pack, right? And now if I'm just gonna hide Ctrl H, and now if I close this, right, go out from here with Tab, for example, and I'm gonna make this a little bit more, condensed. Then if I see this, right, it's here, but if I want to iterate this over, then it does work, but I mean the C, where do I get the C from? It has to be the same thing that's coming in from here. This is the reason why we just don't put the Z here, right? This gets strange, right? So what we have to do is to drag from the C socket all the way to the end, the same thing. I mean, this doesn't get modified alongside the way, right? As you see, it's the same thing that's coming in, it's going out, right? So unlike the Z part, or the Z, which is actually getting some crazy multiplication going on, right? So I'm gonna go out from here, and I'm gonna drag the C here, and the C changes, right? Before, and now it's after, right? So how do we actually see what's going on here, right? Let's use a vector math node, right? So if you calculate, for example, the length of the normal object coordinates, what we get is a thing like that. Which is basically the length alongside the x-axis and the y-axis, and this gives us a circle, right? So if I take a less than node, so if the length is less than, for example, 0.5, this will get white, right? So now we have this circle here in the end, in the center. Now if I do the same thing with our modified coordinates, which are already starting to look like a Mandelbrot, right? Then we should get a rough shape of the Mandelbrot. And let's see how this looks. Do something like that. And this does not look too much like Mandelbrot actually. So, or it actually does. I was getting nervous, maybe I did the math wrong, but I didn't. We have this little dot here. And I mean, if you change the iteration, you see it is kind of looking already like the shape of the Mandelbrot, right? It is similar, right? It just has very little iterations. So let's do so that we take those two, right? We move them on the side here, and then we plug them here. And now we do Alt right click, and we do like that, and then we plug the C into here. And now we already have more iterations, right? So this is pretty cool. So I'm gonna do so that I'm gonna add like 8 of those, right? And then I'm gonna group those again. So Alt right click drag here, and then we can see this, right? This is already Mandelbrot without any doubt, right? So what we can do is that we can, group those things again. And if you want to have something like a crazy amount of iterations, so for example, this would be so that we add, let me think then. All right, I'm gonna add a reroute and a reroute for those two inputs. And then I'm gonna add, right, I'm just gonna group those like that, Ctrl G. And I'm gonna switch the inputs here, Z and C, just, for visual clearance or clear being, whatever. And I'm gonna output them like that. All right, and now I have this one node group, which has 8 node groups, from which each one is our Mandelbrot, right? And now I'm just gonna call this the Mandelbrot with a typo, of course, the Mandelbrot, and I'm gonna iterate this again like that. Now this gets 8 iterations done with each time, right? And this is without the doubt of Mandelbrot, right? So we can iterate this even more, and now this is an even more complex Mandelbrot here, right? So we don't actually need as much iterations, right? This will get a bit crazy. So I'm just gonna maybe keep this like that. And now what I want to do is I want to give this some colors, right? So you might think, okay, let me take a color ramp and let me color this thing here, and or actually the thing that's come after here. And you cannot do this, I mean, because it's just, we don't have any gradient here that the color ramp can change. We do have one here, which is actually the field for the distance from each center of the iterations, right? And I mean, we can do something here. We could remap this and stuff. For example, with the map range, right? I know we have 8 iterations, so we can put 8 here. And now we have like a control like that. And we can add some different colors here. For example, we can make the first one like blue, and then add some things like that, but this doesn't work very well, right? So to get colors, we actually need a bit of a different approach for this Mandelbrot, right? So what I'm going to do is I'm going to go to the very first iteration thing here, like the core of my system, right? And I'm going to visualize that, right? So what I'm going to do is I'm actually going to calculate the length right inside my core, right? So I'm going to take my vector math nodes, and I'm going to calculate from the end the length, which looks like that for the first iteration. And then I'm going to do so that on each iteration, I'm going to add back the length of the last iteration, right? I'm going to add iterations on top of each other so that I actually form the shape of the Mandelbrot, right? So to get the length, first I'm going to output this as an actual output instead of this temporary viewer here. I'm going to call this the length, right? And I'm also going to need an input called the length, right? Because I have to get the length in from somewhere. So I'm going to just do like that. And I'm going to drag here. And I'm going to put this like maybe very, very, very much on top here. And maybe I can also switch those for clear visibility, and this is pretty much done, right? So this means that now this length is going to go out here, and in a new node group, it's going to come in from here again under the name length, of course, and it's going to go out from here. It's going to be added to the new length, and it's going to be repeated over and over and over again, and we are going to have a nice thing, right? So you see now we have those length things here, right? So I'm going to put the first one to 0, and I'm going to alt right click drag and drag over those. Be careful to connect the right things. It's very messy to fix afterwards. And we also have to output the length from here, of course, again, because we are in another node group. So I'm going to put length here. And we also need an input length, right? So this is how it works. And then we'll go out from this node group again. And now we have this length 0. And how this looks is something not very interesting. I'm going to add those together, and this looks, I mean, what is that? Well, the reason is that because we have currently like 16 iterations, right? 8 iterations inside of each node group. We basically have the maximum value of 16. So this means it's like very blown out, right? It's very, very bright. So to get something good out of it, we just have to use a map range to map this to a real and to a nice range of 0.1, right? We have 16 iterations, so we put 16 here, and you see we have this Mandelbrot gradient, which looks a bit different from this one, actually more clear and more beautiful, let's say. So now we can take the color ramp and we can see how this gradient works, right? This works until the ends very nicely, right? Very nicely, really. So this is actually the way I did this flowing Mandelbrot in my intro, right? This looks pretty similar. I think you agree with me, right? As this like scene here. So right, let's add colors now. So how do we add those? Well, we can do, for example, so that I mean it's pretty simple actually. So I'm just gonna make the center. I want this to be, let's say, something like golden, something like that. And then the edges I want to be blue, right? But you see also the thing around the Mandelbrot changes color, so we have to mix this. Basically, we have to determine the outside of the Mandelbrot and mix this to be black, right? Or any other color that you want. I want this to be black right now. So how do we do this? I'm just going to use a mix RGB node, right? And now I can mix between, for example, Mandelbrot and black color, right? I just need the factor to be something that is white, has a white value where I want to let me repeat this, right? So I need to have this factor differentiate between the Mandelbrot and the outside, right? And we can get this from this length here, right? So I can just see how this looks with the threshold of 2. It is exactly the border of the Mandelbrot. And now I can just put this as the factor here, and let's see how this looks. This makes the Mandelbrot black, right? Which is not what I want. I actually want this to be inverted. So we can either invert the factor, or we can just switch the inputs here and do something like that. So this is, I think, an easier way. So now we can make the edges blue, and we can switch this to hue saturation value, for example, and do some things like that, for example. I mean, to change the color of the edges. There are also other cool things you can do. For example, you can take a math node, right? And you can put this to a sine function. And because this is essentially a field of distance, this creates a really good flowing effect. So if I increase the 2 max here, currently the sine is a bit, you know, it has a little bit too low of a range to work with. So you increase this one here, you see we get a thing like that on the surface of the Mandelbrot, which is really cool, right? So it is like, basically shows us the distance function of this Mandelbrot, right? Which is a signed distance field. If you want, you can learn more about those. So I'm going to show you like SDF. It is, I can put the SDF field here. Right, so you see the signed distance field is basically like the distance from an object, right? So, over here you see this, right? The distance of a cube and so on. So this is the signed distance field of a Mandelbrot, and you just made this, right? And yeah, you can use this for colors too, right? You can do something like that, and let's see how this looks. Looks interesting, I think. But you know, I just feel like, and I want to do this right now. I want to add a material, right? I want to add some displacement so that it is like out from the surface, right? So this is going to be exciting, right? So to do this, what I need is first, of course, shader. I want this to be a nice and luxurious metal surface here. I'm gonna switch actually to cycles. Not a huge fan of EV, but you know, actually I think EV can work well, but we're gonna use displacement, so it won't be a nice idea. I'm gonna use this HDR here because this is really a luxurious one. You can see why. And I'm gonna connect the color to here for a moment, and I'm gonna also take down the roughness. And you see, I mean, we have something there, but it's not out from the surface, right? So the question is, how do you get it out from the surface? Well, it's pretty easy. We just need a displacement, right? So displacement, we put this here. Then we are going to add some subdivision here a little bit. And then we're going to go here and add a subdivision surface modifier. Maybe even subdivide this a little bit more to get rid of those very smooth edges here. And I'm going to go to experimental features, cycles, and turn on adaptive subdivision, right? And I'm going to see this again. Of course, no difference here. And I'm going to go with material settings to the material settings, call this Mandelbrot. And under this settings here, I'm going to go to, instead of bump only under displacement, I'm going to go to displacement only, right? So displacement, or I can actually do displacement and bump, right? So, right, let's connect the displacement here. And now you see displacement, what does it do? Well, if we change the mid-level to like 0, for example, and we can change the height, you see it moves up, right? Pretty simple. And what I want to do is I want this to move up only where the Mandelbrot is, and also have some, you know, some smooth edges and stuff like I showed you in the beginning of this video. So this is actually just this gradient here. But you see it has some weird edges here and things like that, which is not very good, I think. So we could basically do the same thing that we did with color. So everything outside the Mandelbrot, we're going to turn into black, right? But I'm just going to show you how this looks right now. So I'm going to connect the result to the height, right? And let's connect to our material, and you see this looks like that. Well, definitely not what we want. Of course, it's inverted, so the edges are higher than the center. And if you think why it is like that, I think it's pretty clear because, I mean, if we start from the center of the Mandelbrot, the distance to the edge gets larger and larger and larger. And because it's a fractal on the edges, the effect gets even more extreme, right? So this is why it is like that. I'm going to put the scale to 0.1 right now. And this looks already pretty interesting, actually. But I think we need a bit of a different thing. First is add more resolution, right? So you currently see the final scale is render 1 pixel, viewport 8 pixels. So it's gonna subdivide the plane so that each 8 pixels is gonna have a new like face or the amount of detail, right? So I'm gonna go to subdivision settings and turn this down to like 2 pixels. And let's see this again. Now you see on the edges here of this Mandelbrot, we have some weird looking like black things, right? So the question is, why do we have those? Well, the reason is, of course, obvious. Because of those, look at this gradient, right? So we need to get rid of this white area here. And for that, we can use same mix node, right? We can take this thing and we can mix this with black. This means no displacement. And we only want to do this when there is the less than node, right? And switch those inputs. Do like that. And now this has removed, as you see, the white part here because of our factor of the, distance factor, right? So let's see how this looks right now. Now this looks better, but it's inverted, right? Am I using my GPU? For some reason, it's pretty slow. Maybe I'm just, recording my screen. Maybe that's the reason. So I'm going to do so right now that I want to invert this, right? So under this map range here, what I can do is I can invert this 1 and 0 and 1, right? But this will mess up my color here, right? So I'm gonna add a new map range. I'm gonna drag from the length here. I'm gonna put this here. This will look the same thing. And I'm gonna put 1 here. So now this will be 1 everywhere. I'm gonna put 0 here. Now this will be inverted. And look at that. This looks definitely better. I'm actually gonna remove the colors right now because this is, this is not very good. I'm gonna add some metalness here and look at that. This looks pretty cool, right? Like really, really cool. So now what I want to do is I want to add some iridescence to the edges here, just for the example, so that you really get the grasp on how to use colors on this fractal, right? So the colors come from here. As you see, they are like that. The edges are currently black. I'm gonna make them, brighter again. And this already looks pretty good. And I mean, I can, of course, like switch them up and do the things that I like here. And you can also use textures on this Mandelbrot, right? Which is really cool because, as you remember, we have the length, but you also have the vectors for this Mandelbrot. So for example, if I were to take, for example, a checker texture, right? And connect the Z to the vector, look at that. We have this mapped beautifully in the most correct way to the Mandelbrot, right? So I can change the scale here. I can make this smaller or larger. I can even use image textures and it's gonna look pretty okay. I'm just gonna show you one, right? I think I have like a bark texture or something like that. Here I have a Buddha Brot texture, which is another version of Mandelbrot. Cannot make this one with Blender actually. Under downloads, let me see if I have a texture here. Bark, right? Bark color, and looks like that. I'm gonna connect the Z to the vector and look at that. This looks pretty nice, right? Pretty interesting. Of course, on the edges, it's gonna get infinitely small, but nevertheless, the mapping is pretty good on the edges, right? If I were to use just texture coordinates, this would look, pretty bad. Texture coordinates, where are you? Texture coordinates, this will be just like slapped onto this model, right? Like there is no difference between this Mandelbrot and anything else. But if I use this, the texture takes the shape of the Mandelbrot, which is really cool. But we are not going to use any texture right now, and this is actually the result. Now, what we're going to do is that we're going to deal with Julia sets and burning ship fractals. So, Julia sets, right? I'm going to show you how they look. They look like that. And this is actually really easy to make, right? So there is even like a map with Julia sets. All right, that's interesting. And you know, they basically look like different, like dragon fractals or something like that. I wonder what is the right, and then we're gonna deal with burning ship fractal, right? Which is a even easier thing than actually Julia set. And this looks like that. It's an infinite ship fractal, really, right? Oh, someone has made a different version, right? I don't actually know the formula of this, so I'm gonna pass on that one. But let's make the burning ship. I'm gonna, or the Julia, and I'm gonna turn off the displacement for now, right? And I'm gonna look at this from here, maybe switch the HDR to something like that. All right, for the Julia sets, how do we do this? Well, the Julia set is basically the Mandelbrot, but instead of the C being the location of each point we calculate the Mandelbrot for, right? It's always going to be the same number. So if you just remove this, it's going to be a big flat old sphere. But if you add some different numbers here, now it's going to turn into a Julia set, right? So we have those things, this strange like H's here, and I don't actually like those. We can like fix those in two different ways. I'm gonna first see if adding iterations works for this one, right? So I'm gonna shift right click drag over here, and I'm gonna add a new one, right? Do like that, and connect the length here. Right, adding iterations actually works pretty well for those. So I'm just gonna add like 6 iterations here. Alt right click drag here, and Z to the vector and length to here. Now, of course, this has done something really weird, right? These are the vectors for this thing. But yeah, this is the shape of it, right? The length C. Now, of course, we have to see how much like iterations we have right now so that we can change this from max value here, right? So we have 1, 2, 3, 4, 5, 6 of those. And in each one we have 8, right? 6 times 8 is 48. So I'm going to put here 48 and also 48. And now it should see something better. And I think it is. Let's see how the colors look. Or these colors. I'm just going to put this one to black. All right. Cannot see this right now. I'm just going to put this to length. All right. So basically the shape of the Julia, we can use some different values here. For example, something like that, right? And the C doesn't, or the Z here doesn't do anything, so we don't have to change this one. But I mean, you can really go all the way crazy here. For example, we can try to make something like that as a displacement. Looks pretty cool, like a dragon, right? So let's see what we can do here. First, we have to create get a normal like distance gradient for us, right? So let's see how this one looks. Alrighty, I'm just gonna actually this one. I'm just gonna try with the color ramp, right? I'm gonna remove this color ramp. I'm gonna re-add this back. I'm gonna see how this works. Is the distance wrong actually? So what I'm looking for with this color ramp is that if I move this black thing all the way to the end, is the whole fractal gonna be covered with blackness, right? Currently it's not, so this means our 48 here isn't working nicely. It seems it actually is, right? I wasn't just looking at this mix output here, and then I got those strange edges here, right? Which actually were removed afterwards, right? And I was wondering if there is like a problem, but actually the 48 works very nicely here, right? We can maybe even, we could actually maybe even lower this, but you know, it's the question of playing, right? So maybe 36 works even better, right? Because I would like this. No, actually, it's not working. 48 is the nice thing. So you just have to play around with this value and see how this color ramp works, right? This is like that, and now I want to displace this right on the surface of this mesh. So let's see how the displacement looks. It looks like that, and let's just connect this here, and let's see how this works. Well, it is pretty massively aggressive, right? All right, it's really dark, so I'm gonna maybe use this one here. Right, it is getting output from here, or it's getting displaced, but it's actually a little bit too strong, right? And I'm also gonna turn down this value here, just so that you can see better what's happening here. So first, of course, the resolution. I mean, I'm gonna re-render this so that has a bit more resolution. And I'm just gonna turn down the scale a little bit more, so like 0.3. And now this is definitely better. But what it has is it needs more detail, right? So I'm gonna go to the subdivision. I'm gonna turn the viewport down to 1 pixel, and I'm gonna see how this looks. It updates the geometry, and now this looks definitely better. Now, of course, I'm gonna use a color ramp to smooth this out a little bit more. This time using like displacement, the one that's going into the displacement, right? So we're gonna see this like that. I'm gonna disconnect the displacement because this makes this thing to calculate over and over again. And I'm gonna like see what I can do here. Alrighty. Like that and like that. And let's see how this looks again. I mean, it's just a game of like trial and error basically, because you cannot go like full on and think it's gonna work. I'm still gonna put this to 2 actually. I'm just looking to like lower the edge of this fractal a little bit. So I'm gonna see if adding the contrast helps, and it does help, right? So this definitely was helpful, and maybe it was even a little bit too much. I'm gonna do something like that and like that. So I'm lowering the edge, but I'm raising the center a little bit more, and maybe even adding resolution. So yeah, basically this is how this whole thing works. It's trial and error. I don't know either what the right values are. And this looks pretty cool. I think you can use this as a like ornament on like a wall or something like that. Like a pretty cool fractal, I think. But it's very detailed, so I'm just gonna switch to something that is actually a bit less detailed, right? So let me preview this length again, and this looks like that. And I'm going to change the shape of this. Just gonna, remove the displacement for the time that we are experimenting, right? I'm gonna show you how to make the iridescent border do it. So maybe like, I think I use the fractal like this one, right? This is a bit less like extreme. So like that and like that. Let's see how this looks. I think the edge is looking fine. It's pretty nice, pretty logical. Now we just have to connect the colors here. So currently the colors and our colors are black and white. So I'm gonna make the in part, that's inside. I'm gonna make this. I'm gonna make this golden again. Remove the displacement because it's getting so slow doing that. I'm gonna go back. All right, so we just have to understand. Okay, the white is in the center, right? So something like that. I'm just gonna move it so that I have the gradient for each Julia set. It's gonna be different, right? So something like that. This one I want the edges to be blue, and I want the inside to be like a golden one. Although it hasn't turned into a golden one. I'm gonna move this blue one back a little bit. Something like that. And you can make this a hue saturation value, so it changes the color like that, or far, or something like that. I actually maybe even like this, right? Let's see how this looks. Displacement, and yeah, it looks like a car tuning like color, right? So basically play around with those. I mean, it's completely up to you how this color will look for you and how you want this to look. And now let's deal with the burning ship fractal, which is just one node added to the Mandelbrot, right? So let's connect the C back here again. Now this is a Mandelbrot with pretty ugly colors, and let's go inside of our core Mandelbrot formula, and after the imaginary, let's add an absolute value thing, right? And this will basically do so that our thing turns into a burning ship, right? So here it is, looks like what kind of a ship, right? Well, the ship is actually down here, right? You see, here is the ship. It's upside down, but I mean, you can rotate the view, it's gonna be fine. And again, you can do the same displacement tricks with it. Really, it's a ship, right? You can see. It's very weird that only adding an absolute value here can change this thing so much, right? And create such cool patterns, right? But yeah, I think you might even have some other ships here, right? Like this one. This is like this, it's a ship, right? So this is the thing. I mean, I'm gonna have the project file in the description, or like you can download this from Patreon. I have this, I think a drive link or just a direct link to it. And yeah, I hope this was useful. And also you can download the Mandelbrot project file. So see you next time. And if you have any questions about the math that I can answer, I will answer your questions under the Patreon post. So see you next time.